In 7.1, we had a lot of reading and a lot of writing, kind of to learn the background of hypothesis testing. So in 7.2, we're actually going to do the calculations. So this should go a little bit quicker as far as not having to have so much background information because we covered that in section 7.1. So what we're going to start off with is using p-values to make decisions. And if you'll recall from earlier, if the sample size is at least 30, and n is our number for sample, so at least 30 means greater than or equal to 30, then we say that the sampling distribution is normal. To reach a conclusion in a hypothesis test, use a p-value for a sample statistic such as the sample mean. When you assume the null hypothesis is true, the p-value of the hypothesis test is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample. So what we're going to be doing is looking at what that means in the context of some actual problems. So we're going to start with, and this was actually included in the last section, if the p-value is less than or equal to the level of significance alpha, then we're going to reject the null hypothesis. And if it's greater than alpha, then we'll fail to reject it. So on example 1, we're just going to interpret the p-value. It says the p-value for a hypothesis test is p equals 0.0237. What is your decision when the level of significance is 0.05 and when the level of significance is 0.01? So what we're doing is we're comparing the p-value to the alpha or the level of significance. So we're going to start with, on 1, we have that the p-value is 0.0237 and the level of significance is 0.05. So all you're going to do is make the comparison. Is this greater than or less than that number? So 0.02 is less than 0.05, so it is less than. So our rule is that if the p-value is less than or equal to, then we're going to reject the null hypothesis. On the second one, still have the same p-value, but this time we're using the level of significance of 0.01. So 0.02 would be greater than 0.01. And if the probability is greater than the level of significance, then we're going to fail to reject the null hypothesis. So that's how we're going to do make our decisions based on the p-value. The lower the p-value, the more evidence there is in favor of rejecting the null hypothesis. The p-value gives you the lowest level of significance for which the sample statistic allows you to reject the null hypothesis. So in the example above, you would reject the null hypothesis at any level of significance greater than or equal to 0.02. So if anything that's greater than or equal to 0.02 causes you to if the level of significance is greater than or equal to 0.02, then you would reject the null hypothesis. On our next example, we're going to find the p-value for the hypothesis test. So instead of them giving it to us, we're going to find it. So if we're doing a left-tailed test, the p-value is the area in the left tail. If it's a right-tailed test, the area in the right tail. And then two-tailed, it's the area on either side. So basically, we split it between the two sides. So this is similar to all the earlier problems that we've done, probabilities and areas and everything. And if we're looking at less than or greater than or on the two sides. So on example 2, we want to find the p-value for a left-tailed hypothesis test with the standardized test statistic of z equals negative 0.23. So they're giving us the z-score, and they want us to find the p-value for a left-tailed test. And then after we do that, we'll decide whether to reject the null hypothesis if the level of significance is 0.01. Okay, so first of all, when we're looking at this, I've again inserted the picture here because it makes it a little easier to explain. So if we want to do a left-tailed test, then we're saying that the area is to the left of negative 2.23. So we're looking at the area to the left of negative 2.23. So we're looking at here that's shaded in blue. That's what we're looking at. So P is equal to the area in the left tail. P is equal to the area in the left tail. So what we're going to do is we're using our z-scores. So that means, once again, we're going to go back to our table 4 that has the z-scores in it, and we're looking for negative 2.23. So negative 2.2, and then we're coming all the way across to 3. So when we look at that, that gives me 0.0129. So 0.0129 is my p-value. And then what we're going to do after we've found our p-value, so this is actually really easy because it goes back just to using that table. And then once we've found the p-value, we're just going to add another step to it. We're going to compare the p-value to the level of significance. So once we've done that, we're going to make that comparison of 0.0129 compared to 0.01. So 0.0129 is just a little bit bigger than 0.01. So since this is greater than, so since our p-value is greater than the level of significance, I'm just going to put alpha here. Since the p-value is greater than the level of significance, we fail to reject the null hypothesis. And of course, here we don't even have a hypothesis that we're looking at, but we will here in the as we move further through the lesson, we'll actually have some problems that we're reading, so we know what the null hypothesis is. Here we're just making sure that you understand how to calculate or find p, and then how to compare it to the level of significance. So on example 3, this time we want a p-value for a two-tailed test. So we're looking at z equals 2.14, and we have a level of significance of 0.05. So I forgot I included these little snippets of the table here, so I don't have to flip over to my other one. So we're looking at z equals 2.14. So when we're doing this, you can see here that we have, if it's a two-tailed test, then we're looking at either to the right or the left of 2.14. The right of 2.14 or the left of negative 2.14. So the area to the right and then the area to the left. So what we're going to do is we're just going to go to the 2.14 in our table. So we'll come here across to the 2.14, and we get 0.9838. Now remember that when you're on the right-hand side, we want to subtract, because the 0.9838 actually gives you the cumulative area up to that z-score. So when you're looking in this table, it always gives you the area below that z-score. So if you want the area to the right of the z-score, that's when we always have to subtract from 1. So the area we're looking at, p is going to be 2 times the area in the tail, because we're looking at, we have a right tail and a left tail, so we're going to find the area in the tail and then double it. Instead of having to work the problem twice, we'll just double the area over here because they match. So p equals 2 times the area in the tail. And then when we have z equals 2.14, then that gives us an area of 0.9838 that we found down here, 0.9838. So in the right tail, the area is going to be, so the right tail area would be 1 minus 0.9838, which would be 0.0162. And then since we're doing a two-tailed test, what that means is that, here's where I marked that. that means that this area over here is 0.0162, and then this area over here is 0.0162. So because of that, we're going to get our probability is going to be 2 times the 0.0162, and that would be 0.0324. And then we're going to compare that to the level of significance. So 0.0324 compared to 0.05. 0.03 is less than 0.05. So we would say, since the p-value is less than 0.05, we have to, or we can, or will reject the null hypothesis. So that's how we find a p-value for a two-tailed test. The next thing we're going to look at is a p-value for a z-test. So we're going to perform a hypothesis test for a mean, assuming the standard deviation sigma is known. And you'll notice that's the title here of this particular lesson was, if you go all the way up to the top, hypothesis testing for the mean when sigma is known. And then we do a different kind of testing if sigma is not known. So we're going to, if we know sigma, then we're going to use what's called the z-test. And we're going to need to find the standardized value for this test statistic sample x bar, which is, of course, the sample mean. And we're using the formula, the sample mean minus the hypothesized mean divided by the standard error. So you'll notice this is very similar to the formula we've been using where we said x minus mu over sigma. But here we're looking at the sample mean, the hypothesized mean, so the mean that they've proposed, and then the standard error. So for the z-test, it is a statistical test for a population mean. It is the test, or the test statistic that we're using is the sample mean. And then the standardized test statistic is the z here. And again, this is one that we've used before. This is when we do standard deviation divided by the sample size. And these conditions have to be met. The sample has to be random. And then just like always, you have to either have a sample size greater than or equal to 30, or the population has to be normally distributed. So that stays the same throughout. And then remember that the sigma divided by square root of n is what we call the standard error of the mean. So here are our guidelines, and this is going to walk us all the way through an example, all the way through a problem. We're going to verify that we know sigma, that the sample's random, and either normally distributed or sample size greater than or equal to 30. That's before we ever start the problem. We verify that to see if we can even do the z-test. Then we're going to state the claim like we did back in section 7.1, the null and alternative hypotheses. We'll specify the level of significance, so that'll be in the problem. So we're going to identify what alpha is. We're going to find z using this formula right here. Then we find the area that corresponds to z using our table that we're very familiar with by now. And then we're going to find the p-value, and that's going to depend on whether we're doing a left-tailed, right-tailed, or two-tailed test. And then we'll make a decision to reject or fail to reject the null hypothesis, and that's based on the comparison of your p-value to the level of significance. And then we're going to interpret it. So like we always do, you need to put it back into the original problem and interpret it, tell what it means in the context of that problem. So on this one we have, in auto racing, a pit stop is where the racing vehicle stops. So we know all of that. The efficiency of the crew can affect the outcome of a race. So we have a pit crew that's claiming that its mean stop time to do 4 new tires and fuel is less than 13 seconds. So the mean is less than 13. That's what they're claiming. So we have a random sample of 32. So we have n equals 32. And that's just 32 pit stop times they tested, and that was a random sample, and we got the sample mean equal to 12.9. So if we assume the population standard deviation is 0.19, is there enough evidence to support the claim at the 1% level of significance, or the 0.01 level of significance? So all I did, and I just wrote these over to the side so that we would have them as we got ready to plug them in. So this was, of course, the claim, but you can also, as far as using it in the formula, we're going to actually use the mean of 13. So these are all the numbers that we're going to be using to plug into our formulas. So we want to use a p-value to determine if there's enough evidence to support their claim that their stop time is less than 13. So the first thing we're going to do is go through the checklist. Do we know sigma? Yes, we know that. Also, is it a random sample? So random sample, yes. And then, is the sample size greater than or equal to 30, or is it a normal distribution? So we have a sample size greater than or equal to 30. So n is greater than or equal to 30, check. So that's the check we're going to go through first. And then once you've done that, that tells me we can use a z-test. So we're going to go ahead and state the hypotheses first. So the null hypothesis and the alternative hypothesis. So remember that the alternative is the one that does not contain an equal. So since they said the mean time is less than 13, there's no equal to, that's going to be the alternative. So the mean is less than 13 seconds, and that's the claim. So that means the null hypothesis would be the opposite of that, greater than or equal to 13 seconds. So those are our two hypotheses. The level of significance they gave us was 0.01. And then we're going to use the z-test. So we're going to find z and write down the formula. So, like I said, this is the same one we've used previously. And we're just going to plug in our numbers. So when we did that random sample of 32, we got a sample mean of 12.9 minus the hypothesized mean, or the claim, which was 13, divided by sigma, which is 0.19, divided by the square root of the sample size, which is 32. So we do all of that, and that's approximately negative 2.98. And we round to 2 decimal places automatically on these because remember we're using to find the z-score, that table is set up for 2 decimal places. So we're going to go to the table, and we're going to negative 2.98. So erase the one from before. Negative 2.98. And when we go to the table, it looks like that's going to be 0.0014. So based on this z-score, we get that p is equal to 0.0014. And to determine the type of test we're using, and that's going to affect our p-value because whether we have to subtract from 1 or not, because it was less than. Remember, less than makes it a left-tailed test. So this is a left-tailed test because the claim was less than. So that makes it left-tailed. So it's a left-tailed test, and the p-value is the area left of z equals negative 2.98. So that's what we found. I'm just kind of going through the steps here and what they mean. We've been doing this quite a lot in the last few sections. So just to remind you what we're finding. So this is the area left of z equals negative 2.98. I've got the picture here. So you see that very small area right there. to the left of that. And then we're going to compare our p-value to our level of significance. So we're comparing 0.0014 to 0.01. Obviously, 0.00 is less than 0.01. So because of that, so since the p-value is less than the level of significance, 0.01, you would reject the null hypothesis. So what does that mean in the context of this problem? So based on this problem, the null hypothesis was that the mean time is greater than or equal to 13. We're rejecting that. So we're going to say there is enough evidence at the 1% level of significance to support, since we're rejecting this one, so we're going to reject that one. So if we reject that one, that means we're supporting this one. Whichever one you reject, you're supporting the other one. So if we reject this one, we're supporting the claim. So there is enough evidence at the 1% level of significance to support the claim that the mean pit stop time is less than 13 seconds. So now you can, we've ran through a problem from start to finish. We've put everything together with the null and alternative hypothesis, the z-test, the p-values, and we've put all that together to show you what the whole purpose of the hypothesis testing is. And of course, like we said earlier in the first section of Chapter 7, this is very important when you're dealing with claims about medicines. If you're dealing with claims about, we did the problem in 7.1 about the contaminated meat. So you can see why the hypothesis testing would be important in cases like that. It's also important to advertisers because they want to, their marketing strategies to market their products, they want to be able to write claims that are true and will be accepted. So on the next one, another problem. It's work the same way, but it'll be a different test. Instead of the left-tailed, it's going to be a two-tailed, and we'll talk about why it's two-tailed. So I'm going to do the same thing I did in the first one. I'm going to write down all the information we know first, and then we'll go back and plug it all into our formulas. So this is a study of U.S. homes that use heating equipment. So in other words, like your heater, or maybe your heat and air unit, maybe a standing heater, but some kind of heating equipment. The mean indoor temperature at night during winter is 68.3 degrees Fahrenheit. And that's according to a study, that's the mean indoor temperature. So we're going to say the mean is equal to 68.3. So that's the, according to the study, that's the claim. You think that this information is incorrect. So in other words, we want to find proof that that's wrong. So we randomly select 25 homes. So since we're selecting 25 homes randomly, that's our sample size is 25, that use heating equipment in the winter. And we find that the mean indoor temperature at night is 67.2. So this is the mean of the sample. So this is the sample mean is 67.2. From past studies, the population standard deviation is known to be 3.5. And the population is normally distributed. Is there enough evidence to support your claim? So the level of significance is 0.05. All right, so the first thing we're going to do, can we run the z-test? So first of all, do we know the population standard deviation? Answer is yes. Is it random? It says we randomly select, so yes. And then on this one, our sample size is too small. It's less than 30, but they told us that it was normally distributed. So since it was normally distributed, we didn't have to have the sample size greater than or equal to 30. So our conditions are met. We can do the z-test. Okay, we're going to go ahead and write our hypotheses so we'll know what we're testing. Okay, so the claim this time is the mean is equal to 68.3. So because it contains the equal to, that goes to the null hypothesis. And then we're claiming, so it says that you think the information is incorrect. So that means our claim is that the mean temperature is not equal to 68.3. And that's the claim we're making. So, of course, and we've already got the level of significance. So we're going to do our z-test. So sample mean minus population mean or hypothesized mean divided by the standard deviation divided by the samples, square root of the sample size. So I'll plug in all of our numbers that we wrote over here. And we put that all in and get approximately negative 1.57. So we're now going to go to our table. We're going to negative 1.57. So negative 1.5 and 7. So that puts me at 0.0582. Okay, and I guess I should have specified this at the beginning, but because our claim is not equal to, that means we could be on either side. So anytime it's not equal to, it's a two-tailed test, and that's because claim is not equal to. So if it's less than, it's left-tailed, greater than right-tailed, not equal to is two-tailed. So we're going to be looking to, since we did the z-score is negative 1.57, that's giving us the area to the left of negative 0.157. So my p-value, we said, was 0.0582. And then since it's a two-tailed test, we have to multiply that by 2 because this is the area left of z equals negative 1.57. But since it's a two-tailed test, then I'm going to have to do p equals 2 times 0.0582. So that gives me a p-value of 0.1164. And then we're going to compare that p-value to the level of significance, which in this problem was 0.05. So 0.11 is obviously greater than 0.05. So because of that, we're going to fail to reject the null hypothesis. So our interpretation would be, if we fail to reject the null hypothesis, so this one is we fail to reject this one. So if we fail to reject it, that means we cannot support our claim. So if we fail to reject the null hypothesis, we cannot accept our claim or support our claim. So like on the previous one, we said we rejected it so we could support our claim. So on this one, because we failed to reject it, then we cannot support our claim. So the way you would interpret this then would be there is not enough evidence at the 5% level of significance on this one to support our claim that the mean indoor temperature at night during the winter is different from or not equal to the claim of 68.3 degrees Fahrenheit. And of course, that's for U.S. homes with heating equipment. So that's how it would look if you were doing a two-tailed test. Okay, on using technology, I included this, but like I've explained in the previous sections, it's really much quicker just to use the table. The only thing, the advantage the calculator has is if your values aren't exactly numbers that are in the table, so it might make it a little bit harder to find them, but you can always get close. And when you take the test, they actually include the value in the answer in their answers, that if you use the calculator, they have the answer put in, so that if you put that answer, you'll be counted correct, or they have the answer that you would get if you use the table, and that's put in. So it really doesn't matter as far as getting the questions right on the assignments and on the test. But if you're going to use the TI-84 calculator to make your decision, here is what you're going to see. So you're going to input your data. So they inputted the population mean, the standard deviation, the sample mean, and the sample size. And then you're going to tell the calculator whether to use not equal to, less than, or greater than. And this is where you're going to do this, is you're going to the z-test. So you're going to perform a z-test on your stats. And then, so what that means is when we run this test, then we end up with a z-score of negative 0.201 or negative 2.01, and then a p-value. So what it does is it calculates the z-score and finds the p-value for us is at 0.04, and then you would compare that with the problem. So in this one, it said the level of significance was 0.05. So our p-value, 0.044, is less than 0.05. So then we would have to reject the null hypothesis. So of course, again, we could find all of this information. It's just that when you're using the calculator, you're not restricted to the 2 decimal places, so you're not having to round as much. But all of these are easy calculations to make without the calculator. But if you want to run this calculation, you're using the z-test in your statistics to run that calculation. Okay, in the next part, we're looking at rejection regions and critical values. So this is another method that allows us to decide to reject the null hypothesis. And what we're doing is we're going to determine if the standardized test statistic falls within a range called the rejection region. So if our value falls in the rejection region, that would be a reason to reject the null hypothesis. So your rejection region or critical region is the range of values for which the null hypothesis is not probable. So the null hypothesis is not probable. If it's not probable, that's called the rejection region. If the standardized test statistic falls in this region, then the null hypothesis is rejected, and we have a critical value z sub 0 separates the rejection region from the non-rejection region. So here are our guidelines for doing this. Specify the level of significance, which they tell us in the test or in the problem. Determine whether we're doing a left-tailed, right-tailed, or two-tailed. find the critical values. If it's left-tailed, we're going to do the z-score that corresponds to an area of alpha. If it's right-tailed, a z-score that corresponds to an area 1 minus alpha. And then two-tailed, we have to split it, so it'd be 1 minus half of alpha. And then sketch the normal distribution and draw lines where the critical values would be. So this is showing you here that if you're doing a left-tailed test, here's our critical value, and we're going to be, our rejection region would be to the left of the critical value. Here, the rejection region would be anything to the right of the critical value. And then here, we split it, and it's in either one of the tails. And it says, note that our standardized test statistic that falls in the rejection region is considered unusual. That's why we're rejecting it. It's because it's considered unusual. When you cannot find the exact value in the table, then like we've done in previous problems, we use the area that's closest. If it's exactly midway between, then we split the values and we use the z-score that's halfway between. So, and we've done that in the previous problems on the test reviews. I've shown you how to do that. So on example 7, we want to find a critical value for a left-tailed test. So the left-tailed test, the level of significance is 0.01. So if it's 0.01, what we're going to do is we're going to go to our table, and they're giving us the level of significance, which is the area that we're looking for. So if they're giving you the area, then you're finding the z-score. So if we have 0.01, you're going in here and you're looking at these little numbers in here, and you're trying to find the one that's closest to 0.01. So here I see 0.0099 and then 0.0102. So that's just one away, and that would be 2 away. So this one's going to be the closest. So 0.0099 is the closest to 0.01. So you're going to come over here and up here to get our value. So it'd be negative 2.33. Negative 2.33. So for this one, our critical value z sub 0 would be negative 2.33. So what we're seeing over here is there's my critical value, negative 2.33. And then the area to the left of that is 0.01. So that's the shaded region here. And then, of course, all of these you can check or work these on the calculator as well. But again, I think it's just as easy to, and it probably quicker to just use the table. Because normal distributions are symmetric, in a two-tailed test, the critical values are opposite. So in other words, what you have on one side, you would have a matching one on the other side because everything's symmetrical. So that's what we're going to be looking at this next one. We want a two-tailed test with a level of significance of 0.05. So that rejection region has a total area of 0.05. So we've got to split that into the two tails. So if we're going to split that into the two tails, then we're going to have to do 1/2 of 0.05 to split it into the two tails. So we're going to do half of alpha, which would be half of 0.05, which would be 0.025. So we're going to go to our table, and we're looking for 0.025 in our table. So 0.025. And it looks like we have an exact one, 0.025. So we're going to come across here, negative 1.9, up to here, 6. So negative 1.96. So we're going to come back over here, and we're going to say negative 1.96. And remember, though, that because it's a two-tailed test, that means we have two critical values. So negative 1.96 and positive 1.96. So you have and the way they write this, I'm not sure how they'll ask it on your homework. They, in the examples, they write it as negative and positive. z sub 0. So because it's a two-tailed test, you're going to split the area to find your z-score, and then you'll have one negative and one positive, which represents one to the left and one to the right, and then we have our areas on the outside in the two tails. And those would be your rejection regions. All right, and these are some critical values. I mentioned this either early in this lesson or another lesson, that because we use these same critical values over and over again, it's sometimes useful to have just this little small table instead of having to go to the big table every time. So instead of going and looking at 0.10 and finding the z-score, it's always going to be, if you have an area of 0.10, it's always going to be 1.28. So are we looking left, right, or two-tailed? And then that's what we're going to do. So these are our values that you'll use. Your level of significance that you typically have would be 0.01, 0.05, or 0.10. So if you have this little table here, that's a handy reference instead of having to use the big table. So I would suggest you make a copy of this and have this along with the full table that we used for in the previous chapters. So in the next part, we're going to use the rejection region for a z-test. To conclude a hypothesis test using rejection regions, you're going to make a decision and interpret using this rule. So here's our rule. We're going to calculate the standardized test statistic z, so just like we've been doing. If that statistic is in the rejection region, it's in the rejection region because we're rejecting the null hypothesis. If it's not in the rejection region, we're not rejecting, so we're failing to reject. And then this is what it's showing us. If z is less than z sub 0, then this area represents that we're rejecting it, and then this area represents when we fail to reject it. And they do that for the left-tailed, right-tailed, and two-tailed. And then again, they're reminding us just because you fail to reject it doesn't mean that you've accepted it. It just means we don't have enough evidence. So here are our guidelines, same as before. Verify all the information, state your claims, identify the level of significance, get your critical values, determine the rejection regions, calculate z, and then interpret your decision. So on example 9, we have employees at a construction and mining company claim the mean salary, so mean of the company's mechanical engineers is less than that of one of its competitors. So they're claiming that the mean is less than 88,200. So, of course, this is going to be the claim, but for the purposes of using our formulas, we're going to use the mean is equal to 88,200. We did a random sample of 20, so n equals 20. Mean salary of the sample is equal to 85,900. Assume the population standard deviation is 9,500. And the population is normally distributed. And then our level of significance is 0.05. So we have all of that. Now notice that it said that the mean is less than. Less than represents left. So this is going to be a left-tailed test. And of course you can see that here in the picture. So first thing we want to do is verify that we can use a z-test. So we know the population standard deviation. It says it was a random sample, so it is random. And then finally, either the sample size is greater than or equal to 30, or it's normally distributed. And this time they said it was normally distributed. So because of that, we can use the z-test or the z-score, find the z value. All right, so let's go ahead and state our hypotheses. So the claim was that it was less than, and because it's less than without an equal to, that's always the alternative. And that's the claim. The opposite of that would be the null hypothesis greater than or equal to. And then we're going to calculate our z-value. So plug in the numbers that we've already written down. And this comes out to approximately negative 1.08. Okay, now this next part, we're going to save a little bit of time because we know that we were performing a left-tailed test and the level of significance was 0.05. So we're going to go to our table, the little mini table that we looked at before. So we had a level of significance of 0.05 and we had a left-tailed test. So since it was a left-tailed test, we have negative 1.645. That is the exact same value you would find if you went to the big table and calculated it. But so this little table just helps us, instead of having to look at the big one, these are our commonly used values. So once we have that, we're going to say that we have a left-tailed test. I'm just writing down what we just found and how we found it. So we have a left-tailed test. We have level of significance at 0.05. So that gives me the critical value, which we call z sub 0 of negative 1.645. So what that means is, because it's a left-tailed test, we're going to reject anything to the left of that. So we are going to reject, our rejection region will be when z is less than the critical value. Because it's a left-tailed test, we're going to reject when it's less than. So we've got our standardized test statistic z up here is negative 1.08, where the rejection region is negative 1.645. So if you come over here and look at this, here is the critical value, negative 1.645. Here is the rejection region over here. But our z value is negative 1.08. So negative 1.08 is like right here. So that falls not in the rejection region. So because it doesn't fall in the rejection region, we can't reject it. So based on this, and I'm going to go ahead and write this. Kind of put all this together. So z equals negative 1.08, and that is not in the rejection region. Because the rejection region, if z was less than negative 1.645, negative 1.08 is not less than that. So z is not in the rejection region. So here is our interpretation. Since we're not in the rejection region, there is not enough evidence. There is not enough evidence at the 5% level of significance, because that's what they gave us. And remember what we're looking at up here. So that's the null hypothesis, the alternative hypothesis, and we don't have enough evidence to reject. Remember, what we're doing is we're either rejecting or failing to reject. So since there's not enough evidence to reject, or there's not enough evidence at the 5% level of significance to support our claim. So since we're not in the rejection region, we can't reject. So I'm going to write this up here. So if we're not in the rejection region, we fail to reject the null hypothesis, which means we cannot support our claim. If we're not in the rejection region, we fail to reject the null hypothesis, which means we cannot support our claim. So the way we would write that, there is not enough evidence at the 5% level of significance to support the employee's claim that the mean salary is less than the 88,200. All right, and then our final example, on example 10, still doing hypothesis testing using rejection regions. You'll notice on each one of these there was at least 2 examples of each type of problem, and that's because they're wanting you to see the different tests, whether it's left-tailed, right-tailed, or two-tailed. So on this problem, the researcher claims that the mean annual cost of raising a child, so mean, raising a child age 2 and under by married couple families is, so that's equals, $14,050. So they're claiming that the cost of raising a child from birth to age 2, the mean cost is $14,050. In a random sample of married couple families in the U.S., the mean cost of raising the child was $13,795. So this is it was in a random sample, so this is the sample mean. And the sample consists of 500 children. So n equals 500. Population standard deviation is 2875. Level of significance is 0.10. Okay, because it says that the mean equals 14,050, then our rejection region would be not equal to. So if it's equal to, it's right there in the middle, and not equal to would be anything on either side of it. So because of that, this is going to be a two-tailed test. So we have our two-tailed test. We have all of our information written here. All of our conditions are met because we know the population standard deviation. It was a random sample, and our sample size was definitely greater than or equal to 30. So our conditions are met to use the z-test. So we're going to start with our hypotheses. Okay, this time it said the mean was equal to, so that goes to the null hypothesis because of the equal to. And that was the claim. So the alternative hypothesis would be that it is not equal to $14,050. Okay, so you can go ahead and find the critical values now, or you can do it after, like I did on the previous example. I'll go ahead and put them in here now. So we've got a two-tailed test. And we have a level of significance of 0.10, and then either going to the large table and finding the z-score that corresponds with point. Actually, we're going to do a two-tailed test. So when we get there, this will actually have a positive and a negative, but it's easiest just to find the one that corresponds with 0.10. So you can go to the big table, find the z-score that corresponds to 0.10, but again, it's much easier to use that small table that has the numbers already in it. So when you look at that table at the level of significance of 0.10, we have two critical values because it's two-tailed. So you have the negative z sub 0, and that's given as negative 1.645. And then you have the positive z sub 0, which is positive 1.645. And if you'll notice, I want to point something out. I'm going way back up here, but I want to point something out to this for this. You'll notice if you're at 0.5, you're seeing 1.645 and negative 1.645. But our level of significance was 0.10. But remember, when your level of significance is 0.10, you're actually splitting it between the left side and the right side. So when you're looking at this, you're going to have 0.05 over here and then 0.05 over here. So even though our level of significance is 0.10, because it's a two-tailed test, we're actually looking for the values for 0.05. So that's why our level of significance 0.10 is giving me the values from the 0.05. So when we do this, we have our critical values. So now we want to find our, do our z-test so that we can compare that z value to the critical values. So same formula we've been using every time. And plug in our numbers. And this comes out to approximately negative 1.98. So remember what the z-scores are. This is the rejection region. So our rejection region is anytime z is less than negative 1.645 or z is greater than positive 1.645 because we had to split it between the two. So, and this is showing you what I showed you earlier, that it was the 0.10, but we had to split it, and that's why it's the 0.05. So our rejection regions are anything to the left of negative 1.645 or to the right of positive 1.645. So our value that we have, that value is less than negative 1.645, and they even put it here on the little graph. That would be about right there for the negative 1.98. And so it is in the rejection region. So our value is in the rejection region, which means that we can reject the claim. So if we look back up here, this was the claim. And remember, we're always rejecting or failing to reject the null hypothesis. Well, our z-value fell in the rejection region, so we're going to reject the null hypothesis. So if we reject the null hypothesis in this problem, that was the claim. We're going to reject the claim. So our final statement here would be, there is enough evidence at the 10% level of significance this time to reject the claim. And then you always want to state what the claim was. That the mean annual cost of raising a child 2 and under and then by married couple families and all of that is $14,050. So according to our evidence, we could reject that claim that the cost is $14,050. Now, we don't know if that means the cost is less or greater than. We're just rejecting the claim that it's exactly equal to $14,050.